If you got the YouTube stream started, go ahead and pull up the PowerPoint slide.
Okay.
Have you guys tried to see if you can get the interference fringes in either the Newton's rings or the slides show up on a camera?
We haven't. I'm doubtful, but if we get a bright enough light, we might be able to.
Well, it's part of it's the it's more the angle than anything else. So I'm going to pass around these two.
Okay.
And if you could try to position these.
Yeah.
I mean, this, the glass slides, I think you can probably get.
Yeah.
But the Newton's rings might be a bit more iffy. Okay, folks, it's about that time. Thanks again for joining us today. And where we left off on Monday, we had this question posed about what would happen to the image, the real image formed on a screen from a converging lens, if we cover half of the lens. And I would like to open up for discussion. We had defenses presented for either B, C, or D being correct. And those are the only possibilities. I'm just going to not consider the others. So it's all between B, C, and D. And I'm hoping that you've had a chance to think about this a little bit. Does anybody have any additional thoughts beyond what was discussed yesterday? Or if anybody's, does anybody have any thoughts to share on whether or not B, C, or D is correct? Anyone?
I like the answer D, just because if the lens is converging like that, the light will converge to one point. So I think the higher part being covered will just make the bottom half disappear.
Okay, because the image is going to be inverted, is what you're thinking?
Yes.
Mr. Hayes?
Yes. I think the
I
image.
don't have anything to add to that. Maybe for C or B. Mr. Crossgrove?
Well, I've actually changed my answers. I now think it's B because the lens is capturing the full image and it's projecting it, and the focal point is where the lens or the sheet is for the entire lens. But if you cover half of it, the full image is still going to be projected. It's just not going to be as bright because it's not fully passing through the lens.
Okay, so if you didn't hear what Mr. Crossgrove said, in that light from every point on the object is still going to pass through part of the lens, even if half the lens is covered. And that light will still be focused on the screen. to form either the full bottom or the full half, pretty much everywhere. They're just not as going to be as much light, and so it's going to be dimmer. Is that a fair?
Yeah.
Okay. Anyone want to add something to defend maybe C? Well, you've heard some defenses. I don't think we need more discussion. So go ahead and show up your cards and go ahead and hit a letter on chat. Interesting. My recollection from yesterday is it was mostly C and D. Is that your recollection as well?
I believe so.
Okay. Yeah, we've had a change in attitude. The majority of the class is now going with B, in that the image will just be dimmer. And that's a turnaround from yesterday when most folks in the class, well, people did choose B, they were in a minority. C and D were far more popular. And it looks like from this, D is more popular than C, with B being the most popular. But yesterday, it seemed like C was the most popular response. So, again, science is not a democracy, and the ultimate authority is the laboratory. So let's go ahead and just demonstrate this. If I cover the top half of the lens, I still see the full image, but it's not as bright. Does everybody see that? All we do is make the image a little bit dimmer. So is that showing up okay on the video?
Yeah.
Okay. In fact, if I were to cover the bottom half of the lens, you see it's the same effect. We just get the image dimmer. In fact, I could cover all but just a teeny chunk of the lens. In fact, if you could pan the camera up so that people see how little the lens is being, the lens, Colton.
What was that?
If you could show them how little of the lens is still exposed, that's a good word. It's still quite clear that we get a full image, even though there's only a sliver of the lens uncovered. And it doesn't matter which sliver of the lens, which part I don't block. All it does is just change the brightness of the image. Okay, let's get the lights back on. We can go ahead and move that now. So one thing to keep in mind is that every point on an object acts as a source of light if there's light being reflected off of it, or in this case, if it's a source of light. And even if there's only a teeny piece of that lens exposed, light from every point on the object is going to pass through that lens and still be focused at the right spot on that screen. Okay. So I'd like to move on to the next chapter to talk about interference, in that we talked about interference of sound, in that sound is like a wave. Well, historically, the initial descriptions of light revolved around thinking of light as being like a particle. But starting back in the 16 and 1700s, folks started noticing that the particle model of light didn't explain a lot of phenomena. In fact, it looked like light will interfere and diffract are the terms that we use. Basically, it bends when it goes through either small apertures or openings or around a sharp corner. And that's something that we see with wave behavior, in that starting in the mid-1600s, folks were starting to describe light as if it was a wave. And there was a whole bunch of explanations as to why, if we think of the wavelength as being very, very short, in many cases, light will behave like it's a particle. It'll travel in straight lines and bounce. And there were still quite a bit of holdouts. One of the more famous holdouts was a famous mathematician by the name of Poincare, who thought the idea of light being a wave was just not right, not possible. And to demonstrate that it was not possible, he mathematically showed that if light was a wave, if you had a beam of light hitting a coin, basically a circular object, you would get, according to the wave theory of light, you would get diffraction, bending of light around that, to the point where in the middle of the shadow of that coin, you would see a bright spot and then a series of rings, light and dark rings, due to basically an interference pattern. And he used this to say that, look, this is clearly not something that's ever seen. And the idea of there being a bright spot in the center of a shadow is just stupid. So light can't possibly be a wave. And then a colleague of his said, hey, Poincare, I got something I just really want to show you. And he brought him to a very, very dark room where they'd set up at just the right time of day, sunlight would come in and make a beam and hit a coin that was suspended. And then a great distance away in that room, which was kept very, very dark. They padded everything so there was not even a crack to allow light in. And on the wall, you could clearly see a bright spot in the center of the shadow of that coin and a series of concentric rings. And Poincare stopped and looked at this, made some humming noises and said, see, I was right. I was right all along. Yeah, he was a bit of an ass. And he was then one of the most vocal supporters of the whole wave theory of light after that, because it proved his theory. Okay, but we talked about sources of sound, for example, producing waves, kind of like the wave that we see on these little strips. And if we can imagine two sources of light producing waves like this, where they cross and you get two crests in the same spot, well, the waves will constructively add. If we have a spot where two troughs overlap, we'll also get constructive interference. But if we get a place where a crest and a trough cross, that's where we'll get destructive interference. The waves will cancel right there. And so in sound, if you have two coherent sources like this that are point sources, where you move, you'll hear louder and softer and louder and softer. Basically, there'll be an interference pattern that you can perceive as you move around. We get the same thing with light. And let's go ahead and turn off that projector. Do we have the light on the, we'll start with the single slit.
Yep, it's on the single.
Okay. Let's go ahead and have the laser on. And I need to be right there. So if you can man the lights, we might need to turn all the lights in this room off in order for this to be seen. Basically, we have laser light hitting a very thin slit on this light. Go ahead and turn them off. We're going to need the doors closed. Okay, do I have a flashlight back here? I need the other door completely closed, or the lights on off in that other room. Do you have a flashlight?
There's one on the cart.
Okay, I need a flashlight right here.
There's one on next to the computer.
Okay, light so we can see the flashlight. Okay. Okay, so can we put a, I'm not, is there anything showing up on the screen?
No.
We got a little bit right here. Try removing the diffuser.
I'm going to do that. And for those of you who are trying to watch this remote, as you probably noticed, a lot of these optical demonstrations simply do not show up if you're not here. And let's see. Huh.
Oh, I saw something for a second there.
Well, this is not on the. Okay.
Okay, there we go. We got something.
Okay. So what we have on the screen is a laser light going through a very, very thin slit. So this is basically diffraction, what you're seeing. Light goes through a thin slit and is spread out to the side. And if it's dim enough, you should see not just that central peak right there in the middle, but very faint off to either side, secondary peaks.
Yeah, I see it.
Is that showing up on the screen? Okay, I can't tell from back here.
I don't believe so. Or it's showing up well for people.
Yeah, I can see with my eyes. Let's see, Mr. Crossgrove, Ms. Muro, can you see the secondary peaks off to either side?
I can.
Okay. Yes, my eyes are adjusting to the dark. I can see them too. Is that showing up okay on the camera?
I get the primary and then just two, but it's showing up there.
Okay. Okay. Now, that's a very, very narrow slit. If I can let's see, another hand would be really helpful here. Colton, could you do?
You need to keep.
I need to hold the flashlight and shine it upwards so I can see where the slits are. And if we go to a this is also a single slit. No, it's not. That's not a single slit. Okay, let's try. Get the light up here. Over that way. Problem is telling where we have a single slit. Okay, this should be, go ahead and turn the flashlight off. Is that a lot? Is there a lot of little peaks there? Or is that?
Yeah, I'm seeing lots of little peaks.
Okay, that's not what I was thinking of. Okay, light back on, flashlight. I was looking for just a wider single slit. Let me take that. And those are double slits. I am not seeing.
Here, I can turn the lights back on.
Yeah, I think we don't have the slide I thought. Because I'm looking for single slits. But these are all multiple slits. I don't see that one with just a single slit, except for that one that we started off on.
Are these singles?
Are they?
I think they are.
I don't think so. Well, let's try that. Go ahead and turn the lights.
There's lots of peaks.
Yeah, that's not a single slit. There's a lot of little slits in there. Okay, but at least we had the one single slit. I'm going to try to show you an interference pattern from that was the thinnest slit we had, but from a wider slit. That basically means that you've got that central peak that's even more narrow, and the other peaks are even harder to see. Okay, But,
However, there is quite a few of them.
Yeah, that's a multiple slit. So let's go to a double slit. And we might need a diffuser for this one, or might not. Okay. If I could hold it there.
I'm seeing
Problem is the laser, if it moves just a little bit to the side.
I'm seeing a big peak in the middle and then a lot of little peaks, but the peaks themselves are actually oscillating in intensity themselves.
Okay, so what you're seeing is a global pattern. We have a large central kind of where there's several fringes that are. I'm wondering if it would be better if I had, no, that's actually okay right there. Okay, so what you have here is you have a diffraction pattern, which is the large central maxima plus secondary maxima to either side. But then within that, you've got an interference pattern. And so the overall brightness of the light from each slit would make, normally, if the other slit wasn't there, a diffraction pattern where you have a broad central peak and then secondary peaks. But if they're superimposed, we get that interference between the two slits. And so we'll get a broad central maximum, but within that, a series of fringes that are evenly spaced. And then they'll get dimmer and then brighter again when they're within the secondary maxima and so off to the side. And so that's what we see there. And if we have multiple slits, like 3 or more slits, well, we'll start to see, instead of a regular pattern of this interference where it's like bright, dark, bright, dark, bright, dark, we'll see a bright, dimmer, dark, dimmer, bright, sort of pattern, where the interference patterns will not be just a series of bright spots, but bright spots with dimmer spots in between them. Because you could get constructive interference off of 2 slits, but destructive off of a third. And so let's see if I can show you a pattern like that. Okay, Colton, or did you hold or Braden? Did you hold the light up? And for this, I will probably need the diffuser. Now, which side is the fritz? This side. Okay. Okay, which one do I have on 3 or more slits? I think it's this. It's the center column. The center one? Yeah. That's, I think, more of this one? Yeah, that's more of a grading.
Okay.
Okay, go ahead and turn the flashlight off.
We got tons in there, it's dim, but
Yeah, the problem is with the diffuser, we have a lot dimmer light. No, I'm not seeing much of anything.
I'm seeing 3 tall lines in the middle.
Yeah, let's get rid of the diffuser. Okay, can you have the flashlight back over here again? Yeah, the diffuser's just not working. Let's see.
Oh. Yeah, we got.
I'm pretty sure that's 2 slits.
Yeah.
And
Oh.
here,
Looks like the,
and I think that's,
that looks like a one.
okay, I don't think we're gonna see it very well. Let's go ahead and have the lights back on. So for a diffraction pattern, if we look at intensity as a function of position on a screen, we'll have a bright central maximum, and then the first minima, and then secondary maxima, and then additional minima, such that this width of this central maximum is twice the width of the secondary maximum. And in interference with the thin slits, what you had is you had two patterns like this superimposed, with the peaks offset just a little bit, but that would then give you a bright central area and dimmer secondary areas. But within that, you would have interference. And so if we have we would have a, call it an envelope, and within that, we would get a pattern that looks like this. And so this is what you should have seen for the second pattern, is a series of bright lines that got rapidly dimmer and then went completely dark and then got slightly brighter again. With the region where you had the central area, where you had the first bright spots twice as wide as any other spot off to the side. So that's a classic two-slit interference pattern. And if we have three slits, we'll have a bright spot, one that's not so bright, and then a bright spot, and then one not so. One not so bright. You get a pattern that would look kind of like that, where the brightness of the spots would be alternating and getting successively dimmer as you went out through that central diffraction envelope. And if we went to four slits, we would have two dimmer spots between each brighter peak. And if we went with five, we'd have, three little dimmer spots between each. And if we went to lots and lots of slits, we would get a pattern where we'd get like a bright spot and then nothing and then another bright spot. And if we have lots and lots of thin slits, we call that a grating. And so what I have here is not a grating, but a replica grating. It's basically a piece of plastic that's stretched, long chain molecules to create basically something much like a grating. And if I have a laser light, let's see, we'll want to turn the, will this show up? I think that shows up okay. We don't need the lights, all the lights off. But this is a grating, and we get a pattern like this. So you can see that well, technically, there's probably a couple of thousand minimum little teeny spots between each of these bright spots, but they're so faint you can't see them. And let's see. Trying to get a feel for how far apart those, if I just put this in the same spot. Yeah. And I have a purple laser. Would you expect the bright spots to show up in the same place? No. Because where we get these fringes in interference pattern is where the path difference, say in this case, between the two slits is 0. So right here in the center is where the path difference, the light that goes from one slit to that point in the screen versus the other slit to that screen is the same exact distance. This is like right in the middle. But then over here, this is where we have the distance from one slit exactly one wavelength longer than the distance to that screen from the other slit. So basically we get this other fringe pattern because one light from one slit travels exactly one wavelength farther, and so they get constructive interference. And that first dim spot right here where they cancel out from the beginning, that's where the path difference from the screen, from the slit to the screen versus the other slit to the screen, the difference in that is exactly a half wavelength. So light from one slit travels exactly one half wavelength farther than the other, and so we get completely destructive interference. So that's what's going on here is the light from one slit travels some multiple of a half wavelength farther than light from the other slit. And if that's an even multiple of half wavelengths, we get constructive interference. And if it's an odd multiple of half wavelengths, we get destructive interference. But these fringes show up where we have basically a path difference of a wavelength, and the two wavelengths, and then three wavelengths. And so if we had longer wavelengths, where those would show up on the screen would be farther apart. And if we had shorter wavelengths, they'd be closer together. And so what light has longer wavelength, the green or the purple?
The green.
So there we have green. And here we have purple. You see the purple spots are closer together because it's a shorter wavelength. Is that showing up okay on the computer camera?
Yes.
Okay. And gratings like this are very, very useful because they act as a prism. In that, yeah, the slits are so fine that you can't really see them in the camera. In fact, you can't really see them with the naked eye. They're very, very, very narrow. But we can use this to basically make a prism. And if we were to shine white light into this, where did that flashlight go?
It's right there.
We would have, instead of, spots like a wavelength, like a laser, yeah, it's not going to show up, huh? No, it's not going to show up. We'd have to have like a thin,
A white laser.
well, no, not a, there's no such thing as a white laser.
Yeah.
But in fact, I did this earlier. I had a narrow Remember the slide projector I had where I had the rainbow up on the screen? Well, that was white light shine through a replica diffraction grating. Do you remember the overhead projector? That's exactly what I was doing. I'd have to have a much smaller source of light in order for it to be noticeable. But with the overhead projector, we were able to do that. Okay. So we could also get this interference occurring in thin films. Have you ever noticed the pretty patterns that you might see on a puddle if there's oil on the surface?
Yeah.
Okay, that's an interference pattern. Okay, a classic interference situation is where you've got the oil slick, a thin film of oil on top of water in a puddle. You can have light coming in, and I'm exaggerating the angle here. And that light, you'll get some of that light reflected. Okay? But you will also get some light transmitted. And you'll have some of that light then go into the water. But you'll get another reflection right here. And I'm kind of exaggerating the angle. Okay. So if the thickness of this film is D, I'm going to label these two reflected rays 1 and 2. Ray 1, you just get light straight bouncing off of the first surface. Ray 2 happens when you have the light penetrating the oil, bouncing off of the interface with water, reflecting, and then coming back into air. So ray 2 travels a distance pretty close to twice the thickness of the film, farther than ray 1. And if this 2D is equal to a wavelength, lambda is a symbol we've been using for wavelength. If you remember our discussion of waves earlier, like with sound. If that path difference, 2D, is equal to a wavelength, well, you're going to have constructive interference. And say you have white light, well, that means there'll be spots on that oil film. Say if it varies in thickness, if that 2D is equal to the wavelength, say, of green light, at that spot, you'll get a bright green reflection. If that 2D is equal to the wavelength of blue light, you'll get a bright blue reflection off of that point. Does that make sense? And if this 2D is equal to instead a half wavelength, you will get destructive interference. So the pretty patterns you will see on a oil slick are where you have constructive interference at different wavelengths. And you'll also get destructive interference at other wavelengths. And the patterns will repeat. So if that path difference 2D is equal to the wavelength of green light, you'll get a bright green area. If 2D is equal to twice the wavelength of green light, you'll also get a bright green spot. And if 2D is equal to 3 times the wavelength of green light, you'll also get a bright green spot. And so you'll see all sorts of different colors. It's much easier to note the interference from constructive interference than it is from destructive, because having white light where you just remove one of the colors doesn't change the hue of what you're seeing as much as if you had constructive interference. Does that make sense? But you will see both effects. So you'll see a nice, pretty pattern, and sometimes you can see it move around as, well, as the oil moves or the water moves, and that you get kind of a changing in the thickness from place to place. But we get the really pretty patterns off of thin films because of this interference of light. There is another complicating factor that I haven't talked about. And remember when we talked about waves? So like we have a wave on a rope, and that wave pulse hits a place where that rope is tied to a wall, the wave will flip over. And what was an up hump or a crest will turn over and become a trough. Do you remember that? We call that a phase shift. Well, you get similar phase shifts like that with light when it bounces off of materials. In the case of light hitting oil from air, yeah, the light that comes off has phase shifted, flipped over. But then light and oil hitting water, since water is more optically dense, you also get a phase shift. And so both rays 1 and 2 are flipped over from what they were from the incoming light. And so what I have here is correct. But if we had a different film, say we had a soap film in air, you would have a phase shift on that first reflection, but you wouldn't on the second reflection. So you'd get constructive interference when the path difference was a non-multiple of a half wavelength as opposed to multiples of a wavelength. So you have to worry about phase shifts, but I'm not going to get into that kind of detail on any sort of thing I'd be holding you responsible to, but just be aware that there's a little bit more of a complication in that we can get phase shifts of the light on reflection. And by changing a crest to a trough, that's like adding or subtracting a half wavelength to it, because it shifts, you know, where a hump is versus a trough. Now, let's go ahead and go with the next slide. Actually, no, that's not. I just remembered. I did not talk about the Fresnel lenses. So for those of you who are here, you should have a Fresnel lens. And I'll tell you a story. This is a cool story from history.
Let's go grab them.
Lighthouses were very, very important for commerce. You know, 500, 400 years ago. And it was kind of a bit of an international competition. Which port city, which nation had the biggest lighthouses would be the safest for ships to dock in. And there was a direct correlation between the quality of a lighthouse and the amount of commerce that that port could draw. And the problem is, to make a good lighthouse, you needed basically something that could produce a beam of light. So what they had is they had these gigantic lenses, and they put a light source right at the focal point, so you could get basically a beam of light going off in a direction that you could shine out over the ocean. But you wanted this thing to be as tall as possible. You wanted the beam to be as broad as possible. So that means you wanted really, really large lenses, because the width of the beam has got to be the width of the lens. And how thick the lens is determines where the focal point is. So if you want a focal point pretty close to the lens, which is very, very convenient because that's where you want your light source to be, you have to have a really thick lens. And if you're talking about building this really, really tall tower, you kind of have to have the light source close to the lens. And the closer you put the light source to the lens, the thicker the lens has to be. You kind of see the problem? It's an engineering problem in that the best lighthouse is really, really tall with a huge, thick lens up there. And we're talking about lenses weighing multiple tons. And so getting a tower tall enough that could support that kind of weight and being able to make a lens that big was a horrible engineering problem. And the Queen of England approached one of the more famous mathematicians of the day, a guy by the name of Fresnel, and wanted him to design the best and biggest lighthouse, thinking that it was basically an optimization question. In that, how do you optimize the height of the tower, the cost of construction, the weight of the lens? All that needs to be kind of optimized to get the best lighthouse. But Fresnel realized something quite important. In a lens, you have the light refracting only at the surface. You really don't need all this glass in between. It's not necessary. You just need to have the right curvature in the right spot. And so his lens looked kind of like this, where it was a lot thinner and it had the right curve in the right spot. But because it's not super thick, it has just a teeny fraction of the weight of a comparable lens with the same focal point.
So basically, he just took the edges of the lens and knocked out all the material in between.
Pretty much. And the size of the pieces that he used were basically fist size and smaller. And so we're talking about hundreds of sections, not the 6 or 7 that I've shown there. And if you look at the little Fresnel lenses that we passed around, if you look at it really close, you can see circular ridges. Well, those are those ridges where you have the areas of different curvature joining. And you can run your hand over it, you can feel it a little bit rough. But this is a very thin lens, yet if you hold it up near your book and look through it, you can see that it's a very powerful magnifier.
And one other thing I did, just random observation. I find that it gets the best magnification halfway between your eye and the object you're trying to focus on.
That's because you're putting your eye pretty much at the focal point. Okay, so Fresnel was basically able to think outside the box, and this dramatically changed how lighthouses were designed. And England had the best lighthouses for about 5 or 6 years before other people glommed onto the secret. In fact, they had posted guards around all the lighthouses to try to keep anybody out from viewing it. But it doesn't take long to basically bribe a guard his lifetime salary to let another scientific observer in from another country to be able to see it. So within 5 years, you had other countries coming up with the same design. And so it really didn't provide an advantage for very long, but it's a really cool example of the advancement of science. Okay, let's do that PowerPoint slide. Actually, yeah, let's go ahead and show the PowerPoint slide. We don't have enough time to actually go into this detail, but I want you to think about this so we can have a discussion starting tomorrow. 2 microscope slides in air, illuminated with one color light. That's what monochromatic means. So it's like one color light. And so you don't have to worry about different interference at different colors. It's all just one color light. And you rotate the bottom slide towards the top so that the wedge of air between the 2 slides gets smaller. What happens to the fringes that you see? Again, you see interference fringes because of the thin film of air between the 2 slides. You basically have light bouncing off of the bottom surface of the top lens, and then light bouncing off the top surface of the bottom lens, going back out, and it's those two. As that film gets very, very small, that's the interference you're going to see. You're going to see interference from the light that's bouncing off the bottom of the top slide, and light that's reflecting off of the top of the bottom slide. What happens to the separation of the fringes that you'll see? That's the question. Do they go farther? Are they spaced farther apart as you bring that bottom slide up? Are they going to be spaced close together? Do they not change? Or does it depend on which side of the slide you look at, if you're looking at it from above or below? That's the question. And that's all the time we have. So ponder this, and we'll start off our discussion tomorrow on this point. Thank you for your attention.
By the way, guys, I keep pointing out that the start of the class without a card folder on my desk. I keep having to steal ones from the nearby areas.
Okay.
Thanks.